Good afternoon, everyone. Thank you for joining us. My name is Katie Rowley. I'm with the NOAA Central Library, who is hosting this webinar today in collaboration with the NOAA Technology Transfer Office. A few quick logistics for everyone on the webinar today. You are muted, but you do have the ability to ask questions through the chat and question panel. So please place any questions you have in there throughout the presentations. We will hold the questions until the end, but if you have any technological issues, you can't hear or you can't see the slides, try logging out and logging back in. That usually fixes most issues. If you're still having problems, you can either chat me or you can email library.brownbag@noaa.gov and I will try and help troubleshoot that for you. With those caveats out of the way, I'm going to turn it over to Tiffany House to give the introduction for today's speaker.
Thanks, Katie. Good afternoon, everyone. I'm glad you were able to join us today during these difficult times. My name is Tiffany House, and I am the NOAA SBIR Commercialization Specialist. My office, the NOAA Technology Partnerships Office, and the NOAA Central Library teamed up to organize this series that features NOAA and SBIR-funded technologies. Climate Forecast Applications Network, or CFAN, received an award in FY 2016 from the NOAA SBIR program. This program provides competition-based awards to small companies for R&D to transform their innovative ideas into commercial products. All SBIR proposals must directly benefit the NOAA mission and have excellent commercial potential. The technology you will hear about today is still available as a sole source procurement for NOAA and other federal agencies under the SBIR rules. CFAN has developed a new subseasonal forecasting system. Innovations include extreme event probabilities, ensemble clustering, two-step calibration process, real-time verification, and a dynamic user interface. Judith Curry, president and co-founder of CFAN, founded CFAN to translate cutting-edge weather and climate research into forecast products that support the mitigation of weather and climate risk for public and private sector decision makers. It is my pleasure to introduce Ms. Judith Curry.
Hello, everyone. I very much appreciate this opportunity to make this presentation about our SBIR project on subseasonal weather forecasts. Climate Forecast Applications Network, or CFAN, was launched over a decade ago under Georgia Tech's Venture Lab program. CFAN is a research-driven company that develops innovative forecast and decision support tools for our clients. CFAN's OmniCast is an integrated suite of products that provides probabilistic forecasts for the energy sector on timescales from days to season. We provide forecasts of temperature, wind power, tropical cyclones, extreme convective weather, and fire weather risk. CFAN's OmniCast forecast products are used for energy sales and trading, electric utilities, offshore production, the financial sector, and renewable energy. Several long-standing clients have motivated and influenced our product offerings. The title of our NOAA-funded SBIR project was Probabilistic Subseasonal Weather Forecasts for the Energy and Agricultural Sectors. Today's talk is focused on our forecast innovations for the energy sector during weeks 3 and 4. This slide lists the subseasonal forecast innovations that we've developed and introduced into our operational forecast products. A forecast window of opportunity approach, probabilities of extreme weather events, ensemble calibration, a multi-model approach, and advanced online decision support tools. I'll summarize a few of these innovations before illustrating their applications in our operational forecast products. The forecast windows of opportunity approach identifies windows in time and space when expected skill is higher than usual because of the presence of certain phases of large-scale circulation patterns. I often use a poker analogy when explaining this to energy traders. You need to know whether to hold or fold. In forecasting terms, this is the difference between a forecast with high or low confidence. Our forecasts include both anomalies from the mean and measures of extreme events. Ensemble interpretation approaches include quantile probabilities, ensemble clustering, and creation of synthetic ensembles. Central to the forecast windows of opportunity approach is a provision of objective forecast confidence metrics. Identification of forecast windows of opportunity is guided by historical predictability analyses that are a function of season, location, and circulation regime. Confidence in the specific local forecast is based on recent forecast verification statistics and interpretations of the ensemble spread. Next, I'll show you some examples from our U.S. temperature forecasts that illustrate our forecast products and skill. I'll show results from our 15-day as well as our subseasonal forecasts. This nexus has guided our thinking on the transition needed to produce useful forecast products on the subseasonal time scale. The skill of our forecast products is enhanced by calibrations that correct both bias and distributional errors in the global model forecast outputs. Our temperature forecasts include 3 different types of calibration. A quantile-to-quantile distribution adjustment is applied to each ensemble member using the historical model reforecast. An additional adjustment is made to the ensemble using error statistics derived from the previous 60 days of forecasts. Kalman filtering is then applied to the ensemble mean based on recent error statistics. We then produce a consensus forecast using an adaptive weighting scheme for all of the forecast streams based on the recent error statistics. This diagram shows seasonal forecast skill for our 15-day maximum temperature forecast. The dark blue curve shows the mean absolute error for the ECMWF ensemble mean forecast, and the purple curve is for the GFS MOS forecast. CFAN's calibrated ECMWF forecasts are in green, and the black horizontal curve is the error of the seasonal climatological forecast. On average, CFAN's calibration adds significant skill relative to the ECMWF ensemble mean forecast. And if you look at the right-hand side of the diagrams, you can see that CFAN's calibrated forecast is significantly better than climatology for all seasons except for January, February, March. This indicates predictability into week 3. In addition to the seasonal variability in the forecast skill, there is also regional variability. I've selected several regions and seasons to illustrate cases where CFAN's calibration makes a substantial difference in beating climatology. Looking at the time trend and the error statistics in week 2, you can expect some forecast skill heading into week 3. But by the time you get to day 18 or so, it's pretty difficult to beat climatology, even with all the calibrations that we're using. The challenge then becomes to identify something in the forecast that's useful for our clients on the subseasonal timescale. Even if we could beat a climatological forecast by a few tenths of a degree in weeks 3 and 4, this isn't that much help to our clients. What they're looking for is a way to identify the extreme events, heat waves and cold air outbreaks. We define the heat and cold wave probabilities as a percent of ensembles exceeding the 80th quantile of the observed historical temperature distribution for at least 3 consecutive days. This slide shows the regional ROC verification scores for CFAN's 15-day heat and cold wave forecast during 2019. A score of 1 indicates perfect skill, 0 indicates no skill. The blue curves are for cold waves and the red curves are for heat waves. The solid lines are CFAN's forecasts and the dotted lines are the raw ECMWF ensemble means. The overall skill is higher for cold waves, indicated by the blue curves. Much of the skill comes from the ECMWF model itself, although CFAN's calibrations make a significant improvement. ECMWF performs relatively poorly for heat waves, although CFAN's calibrations improve this substantially, especially in the Western US. And you can see that at 18 days, there's still significant skill for the cold wave forecast, suggesting some skill at least into week 3. Here's a summary of the hit rates and false alarm rates for our heat and cold wave forecasts. A forecast of 20% heat or cold wave probability has a high hit rate, but also a high probability of false alarm. A forecast of 50% probability marks the threshold of a useful cold wave forecast beyond 10 days. And a forecast of 80% probability of heat or cold wave is relatively rare, but there is a low probability of false alarms for such a forecast. Now I'm going to illustrate our cold wave forecast using a recent case study. You may recall the recent cold wave during the second week of May that struck the Northeast and Mid-Atlantic states. A number of cities reported record low minimum temperatures. I'll focus specifically on the forecast for Baltimore, which I selected for the profound reason that it's closest to NOAA headquarters. This screenshot shows the Northeast region cold wave probabilities from CFAN subseasonal forecast initialized April 23rd. This is based on ECMWF forecasts, where the dark blue colors indicate greater than 60% probability. For a subseasonal forecast, a heat or cold wave probability exceeding 60% is fairly rare. Now this diagram shows the CFS-based cold wave forecast for the same period, which includes forecast ensembles from the most recent 4 days. The CFS forecast shows only a weak hint of the forthcoming cold wave. The key to a good heat or cold wave forecast is the probability distribution of the ensemble forecast. I'll illustrate this first for the forecast initialized on May 2nd from our operational 15-day forecast product. The top row shows the PDF from the raw, uncalibrated ECMWF ensemble, with the light green bounding the 90th percentile of the ensemble members. The dashed line shows the climatological temperature, and the blue line shows the actual observations. The red arrow indicates the May 9th forecast. The size of the arrow indicates the distance between climatology and the 75th percentile, represented by the border between the yellow and orange. The larger this distance is, the higher the probability of the cold wave. Now look at the bottom row, which shows CFAN's calibrated ECMWF PDF, using the quantile to quantile distributional adjustment. There's a subtle shift of the distribution downwards, but also a broadening of the overall distribution. The simplest sign of a good probability forecast is that the ensemble bounds the actual outcomes as represented by the blue line. You can see that CFAN's calibrated ensemble does a better job of bounding, particularly for the Tmax, the maximum temperature forecast. Comparing the size of the red arrows for the raw Tmin versus the calibrated Tmin, you see that the calibrated ECMWF PDF produces a higher probability of a cold wave. Now take a look at the same PDF diagrams for the subseasonal forecast initialized on April 23rd for both the ECMWF and CFS. Looking first at the ECMWF in the top row, the red arrows show the distance between climatology and the 75th percentile, indicated by the border between the yellow and orange. The size of the red arrow is much smaller than what we saw for the 15-day forecast in the previous slide, but there's still a clear cold wave signal in the forecast. Now look at the PDF diagram for the CFS. There's essentially no distance between the dotted line for climatology and the yellow-orange border, hence a small probability of a cold wave forecasted by the CFS. With this context, how should an energy trader interpret the April 23rd forecast of cold wave probabilities during the second week of May? Well, the high magnitude of the forecasted cold wave probabilities indicates that a false alarm is fairly unlikely. But there are some other indicators in the forecast to look at also. The next slides illustrate how an energy trader could interpret the confidence level in this particular forecast. To identify whether or not this might be a skillful forecast, it's useful to look at the forecast for the Madden-Julian oscillation and the Global Atmospheric Angular Momentum Index, both of which have forecast skill on subseasonal timescales. For the April 23rd forecast, the Madden-Julian oscillation was in an active phase with fairly good agreement between ECMWF and CFS. The Global Atmospheric Angular Momentum Index, or GLAM, is also showing coherence out to week 3. Both of these indices indicate that the atmospheric circulation is organized into coherent patterns that have some predictability out to week 3. Another thing to look at is the Northern Hemisphere teleconnection patterns. On April 23rd, the forecast for the North Atlantic Oscillation, NAO, the Arctic Oscillation, AO, and Pacific North American, PNA pattern all showed coherent signals for the first 2 weeks. This diagram shows the predictability of the Northern Hemisphere teleconnection indices on subseasonal timescales. You can see that predictability declines rapidly after 2 weeks, although the Arctic Oscillation in blue does have some skill in weeks 3 and 4. The utilities of these indicators is not so much their prediction skill on subseasonal timescales, but rather as indicators of forecast skill when the forecast is either initialized at high index values or predicts a substantial signal in the first week. Before the energy trader decides whether the April 23rd cold wave forecast is the real deal or a false alarm, there's one other forecast tool to look at. This screenshot shows the Baltimore forecast from May 2. Here we display CFAN's consensus forecast, the ECMWF quantile to quantile forecast, the ECMWF Ensemble Mean, the ECMWF high resolution simulation, and the GFS MOS. We also include the 10-year and 30-year climatology. The actual observed value is added to the forecast page after the fact. All of the different forecasts for May 9th performed better than climatology, but nearly all were too warm. However, CFAN's ECMWF quantile to quantile forecast, circled in red right here, actually predicted a minimum temperature of 34 degrees, matching the observed forecast. And the best Tmax forecast was the raw ECMWF Ensemble Mean, which was only 5 degrees too warm. While the overall statistics of CFAN's consensus calibrated forecasts are the best, sometimes another forecast is better. How might you know when to pick one of the other forecasts? Here is the real-time verification tables for Baltimore's May 2nd forecast. For each forecast lead time, we provide information on both the mean absolute error and the bias error for the most recent 15, 30, and 90 days. Let's look at the statistics for 8 days lead time corresponding to the May 9th forecast. Looking at the mean absolute error for both the last 15 and 30 days, you see that the minimum temperature Tmin errors are indeed lowest for the ECMWF quantile to quantile. The quantile to quantile forecast is actually often the best one to use when you're looking at a potential record temperature, since the quantile to quantile calibration allows for extending beyond the bounds of the historical data set. Now look at the subseasonal forecast for Baltimore, initialized on April 23rd. CFAN's consensus forecast performed only slightly better than climatology. I mean, the temperatures were way too warm. For the CFS, the raw forecasts were actually better than the CFAN consensus. So why didn't the CFS forecast predict the cold wave? The next slide explains why. The raw CFS, with only a 12421 filter, has a very strong warm bias. Over the last 60 days, you can see a very strong warm bias here. This results in a large calibration factor for the quantile to quantile calibration, which brings the bias error down and also reduces the mean absolute error. So the end result of all this is that 17 days in advance, CFAN's May 9th forecast for Tmax matches the climatological forecast, while the Tmin forecast beats climatology by 3 degrees, but was nevertheless still 14 degrees too warm. In spite of this very mediocre skill in predicting the actual temperature, we were able to forecast a significant probability of a cold wave that actually materialized. The main take home is this: trying to make deterministic forecasts of extreme temperatures on subseasonal timescales is probably a hopeless endeavor. Probabilistic heat and cold wave forecasts are more useful to decision makers and have greater predictability, provided that the PDFs are appropriately formed and calibrated. Next, I would like to show you a much shorter example of our subseasonal wind forecasts. This image shows the forecast skill for CFAN's ECMWF-based wind forecast. The left-hand figure shows the mean absolute error for forecasts out to 14 days. By the way, this is 100-meter winds that we're predicting. You can see that even at 14 days, there is skill relative to climatology, and CFAN's calibration in green does show some incremental improvement. The figure on the right shows the subseasonal forecast skill. ECMWF has skill out to 18 days, with CFAN's calibration extending that by a day or two. The real value of these forecasts is not so much in the accuracy of the determined forecast of the wind speed. Rather, the skill exists in predicting the probability of above average speeds. On the left-hand diagram, the solid black curve shows the probability of detecting above average wind speeds, and the solid green curve shows CFAN's calibration. With a relatively low false alarm ratio even out to 14 days, we can infer some skill in predicting above average wind speeds into week 3. Here's what CFAN's wind forecast actually looks like. This is a forecast initialized on May 14th for 29 days in advance. I was struck by this case since these maps typically look pretty vanilla and boring in week 4. We see high wind anomalies in northern Texas, the Oklahoma Panhandle, and Kansas, a key wind power production region. So how much confidence should we have in this forecast? Day 29 is definitely pushing the limits, but our forecasts do have more skill for the high wind anomalies. Is this one of those forecast windows of opportunity? Maybe. The MJO is active and the forecast was initialized when the Arctic oscillation was strongly negative. I've checked the subsequent forecasts, and so far they all continue to show a high wind anomaly in this general region for the period around June 10th. It'll be interesting to see how this one plays out. So a quick summary regarding the winds. The ECMWF 100-meter wind forecast shows skill out to 17 days. CFAN's calibrated wind forecasts improve forecast skill, particularly for high wind cases. And clustering around weather regimes helps identify forecast windows of opportunity. Finally, I'd like to describe to you some of the calibration and ensemble interpretation techniques that we're using to extend the predictability of tropical cyclones. This slide shows the forecast for Hurricane Irma in 2017, initialized 11 days before landfall in Florida. The figure on the left shows the track probability PDF from the 51-member ECMWF ensemble. After a few days, the track PDF becomes underdispersed and diffuse. The table below shows only a 30 to 60% chance of becoming a tropical storm on day 7. The image on the right shows CFAN's calibrated synthetic tracks. These are created using hindcast error statistics with a Monte Carlo resampling approach. Using this approach, we created 1,500 synthetic tracks. The track PDF shows a dynamic cone of uncertainty, and already at 11 days before its eventual landfall, you can see that Irma already had its eye on Florida. The intensity probability shows a greater than 60% chance of becoming tropical storm the next day, and a 10 to 30% probability of becoming a major hurricane in the next week. On subseasonal timescales, twice per week, CFAN provides monthly track outlooks out to 32 days based on the ECMWF monthly forecasts. We run a modified tracking algorithm through the lower resolution forecast and perform the calibration using the model hindcasts. This map illustrates the forecast in early August 2010, providing tropical cyclone track anomalies relative to climatology. The black lines are the tracks of actual observed storms during that period, when 4 hurricanes formed and passed through the region where our forecasts indicated a high probability of track density. The monthly forecast shows skill mainly during the Cape Verde season, with storms forming from the African easterly waves and having a long lifespan. In this case, forecast confidence was particularly high owing to the strengthened phase of the Madden-Julian oscillation. So, what are the prospects for additional advances in subseasonal to seasonal forecasting? While forecast calibration is important, I see diminishing returns from efforts beyond what we've already done. The primary skill in subseasonal forecasting appears to be identification of extreme event probabilities through appropriate ensemble interpretation and identification of forecast windows of opportunity. It is advantageous to use a multi-model approach. While the ECMWF model arguably defines a state-of-the-art in global weather and climate forecast models, we look forward to incorporation of additional improved models such as the extended GEFS. I regard the most promising frontier in subseasonal to seasonal forecasting to be hybrid statistical dynamical forecast models. There are 2 general types. The first is the use of global models to predict the primary circulation regimes and then statistical models to translate these regimes into surface weather. The second is identification of relevant circulation patterns using the statistical forecast system, and then clustering the global model ensembles based on these circulation patterns to infer the surface forecast. And finally, there's a broad need for more climate dynamics research on the subseasonal to seasonal timescales. In particular, the global atmospheric angular momentum and global weather oscillation seem largely untapped in research and operational forecasts on subseasonal timescales. We greatly appreciate the opportunity afforded by the SBIR grant to research and develop subseasonal forecast products. There's still much to do on improving subseasonal to seasonal forecasts. We look forward to new SBI opportunities to pursue our new ideas on subseasonal to seasonal forecasting. Thank you.
Thank you so much, Judith. That was wonderful. And we do have some questions coming in. Just as a reminder to everyone that you can place your questions into the question panel, and I will be reading them off. So let's start. Judith, if you wouldn't mind continuing to share your screen there. Our first question is, what? I'm
sorry, something's wrong.
You're fine. I'll let you deal with that before I.
Okay, go ahead. I won't touch it.
No worries. Our first question is, what sort of value do you find in real-time verification during periods of rapid regime transformation?
It identifies, it's one tool. Looking at the most recent forecast for the last 15 days is sometimes more helpful when there's a big regime change. It helps you identify changes in the verification skill, the recent verification relative to what you're probably expecting over the last 90 days. And it also, personally, I mainly use the bias part of it. If it's been running hot on Tmax for the last 15 days, well, then I think, then that gives me a hint. And a lot of these, the biases do change, certainly do change seasonally. They change on subseasonal and even on, daily to weekly timescales. So it's sort of an art to interpreting these for a specific location, but people who've been using the tool for a while find a lot of value in this.
Okay, great, thank you. Our next question, how specific is your calibration? Is it done for a single variable for a given region, for example, the Northeast US, or is it global for all variables?
It's for a single variable for a single location, okay? Yeah, and we have calibration fields for the maps that we do some sort of fancy thing to make a map out of it. But the calibrations are mostly targeted at the individual cities. And for the winds, it's more on a spatial basis for the map because we don't do specific wind farm locations. We calibrate the whole gridded forecast product. But it varies from variable to variable, from time horizon. Precipitation is different than temperature. The 15-day is different than the subseasonal, and so on. You have to pick a calibration that makes sense to your variable and your time scale and your region.
Okay, thank you. Our next question is, which version of the IFS did you use and how many days of hindcasts were used for the calibration?
Oh, okay. We use the ECMWF reforecast. They issue those twice per week. They're for 20 years. We use the most recent one, the current one, the most recent one, and the hindcast from a year ago. So we're using equivalently like 80 years of hindcasts.
Okay, thank you. Next question. What use, if any, do you employ multifractal scale analysis, analytics, sorry?
We don't use those, but for this project, no. No, we haven't used those at all.
Great, thank you. At what lead times are forecasts most valuable to the energy sector? For instance, knowing a heat wave will hit tomorrow might not be useful, but is predicting a heat wave 2 weeks out more valuable in dollars compared to predicting it 1 week out?
Okay, the energy trading happens on time scales from minutes to seasons. Okay, and some traders focus, okay, like if you're a wind energy trader, they're trading fluctuations in wind on time scales of like an hour, okay? Others are trading on different time scales, but like the week 3, they really want week 3. They care less about week 4, but week 3 is really a big deal. But they're trading on all these time scales. They're looking for an anomaly, you know, any kind of anomaly that might make sense to trade on given the other factors going on in the natural gas markets.
Got it, thank you. How does the scale of subseasonal heat wave forecasting vary with time of year?
Cold, again, we do better for cold waves, and we do better in the cold season. The heat waves, not so great. And the heat waves is mainly what you care about in the summer. So the biggest skill is, I would say, in the cold half of the year for cold waves.
Okay, thank you. Next question. What is the sample size for a recalibration? I mean, concerned you are overfitting.
Well, like I said, we use the reforecasts, which equivalently 80. 80 years of data. Yeah, so I'm not sure exactly what you mean.
The questioner added what type of cross-validation is used in the calibration?
Well, we evaluate, and I'm not sure what you mean by cross-validation either. I'm not a statistician, but we look at recent error statistics on time scales from 30, 60, 90 days, as well as the reforecasts. And then we do real-time forecast verification to see how we've been doing. So, you know, if I will ask the lead person who works on this to respond to the question more specifically for you, but that's about all the answer that I can personally give.
No, that's great. Thanks, Judith. I will pass on that questioner's name and email. So our next question, do you look at the national blend of models for comparison? Saw that the GFS MOS referenced, and the MBA has MOS output too.
Yeah, we look at the GFS MOS. Once the new GEFS is ready with hindcast, we plan to incorporate that in to our 15-day forecast as well as our subseasonal, but we haven't been using the other product. But yeah, the issue for an we can't use anything that's experimental and might end at some point. So, you know, we have confidence in adding the GFS or the Canadian model, but not some of these other models that are a little bit more researchy, and there's no particular guarantee that they'll still be around or operational in 5 years.
Great, thank you. We have a more philosophical question. Many in the modeling community feel that NOAA is spending too much money on climate models as opposed to weather models, and the weather models are now being extended out to 35 days in a few months. Any thoughts on that?
Okay, I'm really, really excited about the extended GEFS out to 35 days. I think this is going to be really good. I think generally the community has put too much money into the long-range climate models versus the weather models. But that said, the one climate model that I really like is GFDL. So I don't want to see, so I'm not too keen to see that effort diminished. They do far and away the best job with the ocean, which I think is really, really key. So that said, we need all of the above, but I think really, I think the GEFS and the 35-day time scale is a big deal, and I would definitely support investments in that. The CFS and the seasonal time scale, I have to tell you, we've really gone off the global seasonal climate models. We're doing mostly statistical forecasting on the seasonal time scales and using the ECMWF just to predict like ENSO and the IOD and stuff like that. They're pretty useless for temperature and precip on time scales beyond a month. So investing in like CFS, no, but GFS, yes. And I still, again, I'm a big fan of GFDL climate model.
Great, thank you. We have one question following up on this a bit. In regard to climate models, how robust do you find the CMIP6 in terms of trending?
Oh my gosh, the CMIP6 has really thrown a monkey wrench into things. I thought CMIP-FIP, that looked pretty stable and believable. I mean, there's a bimodal split between ones with relatively low climate sensitivity and ones with very high climate sensitivity. And ironically, the ones with high climate sensitivity, this comes from incorporating, fancier cloud microphysics and aerosol interactions. And ironically, that actually evolves from a PhD thesis from my group by Hugh Morrison. This is the Hugh Morrison microphysics that everybody's putting into their climate models. The issue is in using that for climate timescales, you have to add some additional negative feedbacks to keep the aerosol concentrations and whatever under control. So the CMIP, I think I would go back and keep using the CMIP. We've learned something from CMIP-6, but at this point, for projections, I would stick to using the CMIP-5 models and the ones that didn't get too fancy with their microphysics with the very high climate sensitivity.
Great, thank you. Tiffany, do you have anything you would like to add or any questions? I don't believe Tiffany has any questions. I do have a question though. Judith, what is the future for CFAN? Can you tell us?
Okay, tropical cyclones, we've started working with the insurance industry, and that's changing very rapidly. It used to be reinsurance. Now it's more insurance-linked securities, and it's really much more of a dynamic thing than, just writing the reinsurance contracts in January or something. So that's exciting, and we're making some good headway there. We're developing new products for them, not just tropical cyclones, but they're very interested in California fires. And I think there's pretty good predictability, maybe into the subseasonal timescales. We're developing a new product for fire weather risk, probabilistic, using a number of different indices beyond the US one, and it'll be probabilistic. And the user interface will also be overlaid with population, options to overlay it with population as density, as well as transmission lines. So people have, an idea about what kind of trouble a particular fire area hotspot might cause. So that's the big new push. The other thing is more on the climate timescales. We're getting more interested in like the 30-year time scale, what's going to happen out to 2050. We're working on a very cool project right now for a wind energy investor kind of group who wants to know, that, in the regions that they're investing in, is there going to be wind over the next, 30 years? And this is mostly a natural climate variability issue on those time scales. I mean, the slow creep of global warming, hasn't really done all that much for wind speeds, but it's really understanding when might the next shift of the AMO come, and how are all these things, the distribution is, are we going to keep seeing all these El Nino modicies, or are we going to go back to regular modici, and trying to assess the probabilities of these various things over the next 30 years for the climate factors that actually influence wind power production. So that's sort of a new area for us, which we're pretty excited about to be working in.
Great. We did have a few more questions pop up. The first one is, any plan to use machine learning and AI?
Oh yeah, we've been using that in a lot of our stuff. In terms of our severe weather indices and our, like for tropical cyclones, the project we're working on right now is for rapid intensification, to develop for hurricanes, to develop a better scheme for that. And we're using machine learning and AI, a fuzzy logic approach, to develop those indices. So we definitely are using those techniques.
Great, thank you. One last question about your fire weather forecast. We're asking, the questioner is asking, isn't the risk tremendously tied in with local county zoning laws and urban growth into relatively uninhabited areas, as well as human behavior?
Oh yeah, the human behavior we can't pretend to model. Okay, what we do is just, it's the fire weather risks, hot, dry, and windy, in short. We can identify those kind of issues. We can identify regions of low and high population and where the transmission lines are. Beyond that, we also have a new lightning product, although that's not a big issue in California. It is in some other regions. So, whether a fire occurs can be relatively random, but the fire weather risk definitely, weights the dice, in a certain direction.
Great, thank you. Next question. Do these subseasonal methods have some crossover application in forecasting change on the climate timescale?
Yeah, well, yeah, the whole regime thing and the forecast windows of opportunity and how weather relates to, the Arctic oscillation or whatever, we are using those same insights to figure out what might be happening, for the next 30 years. So all of that sort of does tie together. In terms of calibration, for until the global climate, the local, the global climate models, you run them out for 100 years or whatever, they don't have skill on the regional scales or the decadal scales because they're not getting the phasing of the ocean oscillations correct. So until that gets sorted out, all this fancy stuff that we do with calibrating for Baltimore's temperature and whatever is pointless. That said, if anybody's going to sort that out, it's going to be GFDL, because they're doing the best with the ocean circulations, which I think is the key to the whole thing. But yeah, it doesn't really extend. But I think there's a lot of utility in statistical forecast methods out on decadal timescales. The climate models aren't doing so hot on those timescales. If you're trying to get a climate model to tell you what's going to happen the next 30 years, it's not going to be very useful. I mean, it's really about natural variability, and we're working on a network-based model for the next 30 years where you pull all these things together and look at shifts and oscillations and whatever in a network-based framework. that's the approach we're taking for the 30-year forecast.
Great, thank you so much. I'm going to turn it over to Tiffany.
Thank you, Katie, and thank you, Judith. I just wanted to say earlier I couldn't speak because I was on mute, but it was good to hear about the evolution of your product in such a short time, Judith, and I look forward to seeing more from you in the future.
Well, thank you very much.
Okay, thank you all for joining us today. We are going to give you back about 9 minutes of your day. This was recorded, so if you have a colleague or if you missed the beginning, you can find this on the library's YouTube channel. And if you did have any questions, we can pass those on to Judith for you if you email library.brownbag@noaa.gov. And thank you everyone, and have a wonderful and safe rest of your day.